energy of the system. Let's take a look at how do we solve problem with phase change. Now, remember that within the same phase for solid and liquid, we used the formula of that delta Q equals to mass times specific heat times change of temperature. That is temperature change. Obviously, that is within the same phase. When phase change, delta Q equals plus minus mass times latent heat. Either latent heat of fusion or latent heat of vaporization. Did you see this one does not have temperature involved because I just explained during phase change. This is for phase change. During the phase change, that the heat goes to potential energy. It does not go to kinetic energy. That's why temperature remains constant. So temperature is not involved. Because of that, we have to make choice plus minus. Now remember, the system absorb heat, for example, absorb heat to melt, absorb heat to vaporize, we choose plus. Release heat to condense, release heat to freeze, we choose negative. This equation we don't have to because delta T is final minus initial. If final is lower than initial, obviously temperature drops, the system give up energy, so delta T is negative and delta Q is negative, so will automatically give us positive or negative. But phase change equation, we have to either choose plus or minus. Let's look at this problem. This is a problem, say we have a aluminum cup of 100 grams mass and water inside the cup is 300 grams. Both are at 15 degrees Celsius. Now, we guide some overheated steam. Did you see the temperature of the steam is 110 degrees Celsius? And the normal atmosphere pressure, the steam, it usually is when the water boils, it becomes steam, it is 100 degrees Celsius. So if we want to get 110 degrees steam, we have to heat the steam. So this is called overheated steam. We guide this kind of steam into the system, so the steam bubbled and it will first. The steam will drop temperature to 100 degrees. Then that 100 degree steam will condense, become 100 degrees water, and then the temperature of 100 degrees water will drop. And this two start with 15 degrees, and eventually our system, let's say at 70 degrees Celsius, will stop putting more steam into the system. And that time we ask for how many grams of this 110 degree steam has already been getting into the system. So that's the question. In order to solve this one, we maybe need to do a flow diagram. We say steam start with 110 degrees Celsius, and we should let it go to steam of 100 degrees Celsius. Then we let the steam condense, so become water. But this is the phase change, so temperature still be 100 degrees Celsius, and then we let temperature drop. It's still water, but now end of 70 degrees Celsius. That is what happened to steam. For the alumina and the initial H2O, it start with, they don't have phase changes. They start from 15 degrees Celsius and just strictly go to 70 degrees Celsius. So that's what happened to aluminum cup and water inside. So in order to solve this problem, and we still need to list the equation, okay? Let's look at mass of alumina, C of alumina. For alumina temperature change, final 70, initial 15. By doing so, we know this is a positive term. For H2O, final is also 70, initial is 15. That's positive term. So these two terms, this is a Q absorb 1, that's Q absorb 2, that's positive. Now let's look at steam. For the steam, 110 goes to 100, that is within the same phase. It's still steam. So mass of steam of C of steam, which is 0.48 of calorie per gram per degree Celsius. And change temperature now is final is 100, initial is 110. So this turns negative. So this is Q release 1, Q release 1, Q release 1 happened here. Now, Q release 2 happened in the phase change. During the phase change, release means negative. So we have to choose. We have to choose negative of mass of steam, heat of vaporization, because steam condense, we use heat of vaporization, and that one. So we have to choose this negative release. And then once the steam condensed to water, when 100 degrees water goes to 70, that is the Q release of 3 right here. So this term we don't have to worry, because as you can see, mass of steam, a C of, right now it's water, so it's a C of H2O, final 70, initial to 100, this term is automatically negative. So all three, totally, all 1, 2, 3, 4, 5 add together equal to 0. Okay, so this term is negative, Q release 1, and this term we choose negative. This term is Q release 2, negative. So by combining, we can plug in mass alumina, C alumina, mass of water, C of water. Here's a C of water. Here's a mass of water, C of H2O. And this is a known. C of steam is known. Heat of vaporization is known. This is known. So we can find mass of the steam. According to my calculation, it comes out as 30.9 grams, which means at the time that we stop guiding more of steam into the system and final temperature of everybody is 70 degrees Celsius, we already guided 30.9 grams of initially 110 degrees steam into the system. Let's look at another example problem, that is ice-water mixture. If we have 100 grams negative 10 degrees ice mixed with 100 grams 20 degrees alumina, which is a cup, and 250 grams 20 degrees water, which is the water inside a cup. This time we want to find final temperature. You see, this problem is different than a previous one. Previous one we know the final temperature, now we don't. The problem was with not knowing final temperatures, we cannot decide which one experienced what kind of phase change. Whether there is a phase change, we don't know. So the suggestion is whenever ice is involved, if there's no steam involved, we choose 0 degrees as reference. What does that mean? Let me explain to you. We're going to do this. We're going to let negative 10 degrees Celsius ice raise the temperature to 0 degrees ice. And then we'll let the 0 degrees ice melt, become 0 degrees water. Phase change, temperature remain the same. And we want to know how much heat that for this process needs. Because first of all, is Q absorb 1, that is ice raises temperature. Then Q absorb 2, that's ice melting. And then we calculate how much heat can be released by this warm system, which is aluminum cup plus water inside. So we say that for the alumina, which is we have initially 20 degrees Celsius Al alumina goes to 0 degrees Celsius alumina, and then 20 degrees Celsius of H2O, which is liquid, goes to 0 degrees Celsius is H2O, and see how much heat it can release. So this will be Q release 1, Q release 2, and see how can we balance this number. So for QA1, that is mass of the ice, which is 100 grams, times specific heat of ice, which is 0.4 or 5 anyway, and change temperature, final 0, initials negative 10, so it's 10. So the result, obviously, that is 480 calories in order to do this. And then Q absorb 2, melting. In order to melt all of them, 100 grams, every one needs 79 calories. So we need 7,900 calories heat. So QA1, QA2 need this much. And then let's look at it. For this system, release that is 100 grams of alumina of specific heat 0.22, and then change temperature, final 0, initial 20, and this gives us 440 calories. And for the water, it is 250 times specific heat times changes 0 final temperature initial 20. This gives us that, I'm sorry, here's the negative sign, it's being released. That will give us 5,000. So this tells us our system, the warm one, both drop to 0 degrees Celsius, can only release of, negative only means release, 5,440. It certainly can afford this step, which is bring negative 10 degrees ice to 0, but it cannot melt them all. So what we do is we just say, okay, we will melt partially. So what we have available is 5,440 calories. We let the warm system release the heat and let both of them drop to 0 degrees. We let both of them drop to 0 degrees right here. 0 degrees at 0 degree. And then we're going to afford the first part, 480, this part. And the leftover, we say, is going to afford X gram of 0 degrees ice. Each need 79 calories to melt. And we calculate how many grams that we can melt. As a matter of fact, we find that we can melt 62.5 grams of ice. We can melt that. So initially we have 100 grams, and now that much will be melt, be able to melt. And the leftover, which is 37.5 grams, will still be 0 degrees ice. So eventually this is a ice water mixture. Final temperature 0 degree Celsius.